Okay, let's get started. Hope you guys had a great weekend. I wish it would have snowed a little bit more, but that's all right. Maybe tonight. We finished up stress concentrations, right? Then we started into this idea of combined loading. Now we're going to look at what happens when we don't just have this simple problem of a single load source, right? Either axial load or torsion, right? What happens when you combine them together, okay? Because that's more applicable to the real world, right? It's kind of hard to have elements that just have specifically axial or torsion, or we're going to go through bending, right? The real world's a little bit more complicated, so you need to be able to step through combining all of these forces together and look at all the stresses that these forces create within an element. And then on top of that, once we've figured that out, we're going to jump into stress transformations and really looking at, okay, if we have this combined loading where when we were looking at the loading independently, maybe with axial load, right, the worst case normal stress is just going to be that force over the area, right? Cutting a plane perpendicular. If we were looking at the worst case shear force, we were going to cut it parallel to the applied force, right? Well, when you start adding additional load sources, and now we're going to have an axial load, right, and a torsional load, well, what ends up happening is it's some rotation of our material. You're going to find that we're going to have higher stresses than where we're actually calculating them at. Okay, so that's where we're headed. So with the real world, I had this example for you METs out there, right? The propeller shaft on a large vessel or boat, okay? And then similarly on the CET side, right? If we were looking at something that was combined loading with respect to axial forces, right, and torsional forces, I said we could look at a drill stem. Had an example here of the big retaining wall they're holding back Andesite Mountain up in Big Sky so that their new lodge building won't fall down the hill, right? So they drill a bunch of shafts, fill them with concrete and rebar. They also do big tiebacks where they drill back into the ground. They grout in a steel cable, and then they jack that steel cable from the surface and then put a big retaining wall that we're essentially pushing back on the mountainside also. So we have these cases where we're going to have combined loading, right? So where are we headed? Well, we're headed to this scenario. Right, where we have torsion, axial, and bending. Bending's going to require a little bit more explanation and discussion before we include that, but we're going to start by just including torsion and axial loading, right? So if we start by looking at an example, right? Very simple example where we have a pipe, okay? They've given us the outside diameter and the wall thickness, okay? And it's loaded as shown, so we have two applied torques on this pipe that's fixed at a wall surface, okay? So we have a torque on the end and torque midway down, and then we have an axial load of 25 kips. And they ask us, what is the normal and shear stresses at point K and H? Well, let's start by looking at, okay, if you remember, stress, normal stress, is force over area, right? Shear stress, right, due to torsion, TC over J. Right. So if they want us, in this case, right, figure out what's going on at point K and point H. Any ideas where we're going to start? This isn't a trick question. Do this. Yeah, exactly, right? We need to know what forces are acting at K and at H, right? We need to know these P and the T. C and J can be determined just from the dimensions, right? Same with A. So we really need to know what T and P are So I'm going to start this at point H. I'm going to draw a free body diagram. So in order to figure out what the forces are at H, right? Creating a free body diagram, right? We're calculating internal forces. So I really want to cut this pipe at H, right? I want to cut this pipe. In my case, I'm going to cut it right at the left-hand side of that little square. Okay, so I can highlight what's going on the side of point H. So what does that look like down here? Well, I'm going to do a little sketch of what this would look like. Right, so I'm cutting out the end of our pipe. Right? Cut out the end of the pipe. I'm going to give it coordinates. I'm going to say it's positive x to the right, just like the big diagram there, like we do with every one of our free body diagrams. And then I'm going to start by applying what are the known forces on our pipe. Well, in this case, if we look at that end of that pipe, we have a 36 kip-inch torque. We use the right-hand rule, right? Curl our fingers in the direction of that arrow. My thumb's pointing to the left. So on this right-hand side, I'm going to say that I've got a double vector arrow, which denotes torque, right? Which is just a moment. And this is 36 kip-inches, right? What else do we know about this pipe? Well, it's got another applied force on it, right? If we cut that end of that pipe off, we have this axial force of 25 kips acting at the end. It's going to be a single arrow vector. We're going to call this P equals 25 kips. Right. Well, we know that this shaft's in equilibrium, right? It's not moving. So we're going to have equal and opposite forces on the ends. Call this T2, right? We could call this P2. This we could call P1. This is T1. Right. So if we sum forces in the x direction, right? The forces acting along the x-axis are P1 and P2. Well, that means that P1 equals P2, or P2 equals P1. So we could say P1 equals P2, right? That's sum of the forces about the x equals 0. That's where we got that. We could also go about looking at some of the moments, right, about the x-axis. In this case, we have our two torsional forces, right? We could say T1 equals negative T2, right? Same with up here, sorry, P1 equals negative P2, vice versa. They have to act in equal and opposite directions. We get that from some of the moments about the x equals 0, right? So if we have 36 kip-inches acting to the left, right, along the negative x direction, so it's negative, that's negative 36. That means T2 is 36 kip-inches, right? Positive, if that vector arrow is acting to the right, positive 36. Well, we have our forces on our free body diagram. We can now jump back up and calculate stresses. We need to know area and we need to know J are our two big ones, so I'm going to put those up here because we're going to need them for the other one too. Area, pi over 4 of a pipe, large diameter squared minus the small diameter squared. This is 2.95 inches squared. J, well, it's pi over 32. D to the fourth minus little d to the fourth. J is 10.4 inches to the fourth. And obviously C is the maximum radius. It's a 4-inch pipe, so that's going to be 4 divided by 2, or 2 inches. So we can start by just plugging and chugging all these out. Normal stress is force over area, negative 25 kips divided by 2.95 inches squared. What does that mean? Well, we have negative 8.49 KSI. What does that mean? Well, that means we're in compression, right? Shear stress, TC over J, 36 kip inches times 2 inches, right? That'd be 4 divided by 2, or the diameter over 2, gives us our radius over J, which we decided was 10.4 inches to the fourth. We get 6.92 KSI. So those are our stresses. Any questions there?
Is that 2 inches?
For the radius, yes. Yep. It'd be the diameter over 2, 4 over 2. So that's what's going on point H, right? That was this little square H, right? We can figure out what's going on. We figured out the stresses acting at point H. Well, the force acting towards the surface. We know it's in compression, so it's negative. We're going to have a force acting on the side of point H. We're going to draw a little diagram here in a second, and after we look at K. And then similarly, torsional shear stress, right? This torque is acting clockwise. That means the stress is acting downward on this face, right? So we've got 6.92 KSI for shear stress acting on the side of point H. If we look at point K now, well, we need to draw another free body diagram. In this case, I'm going to draw a free body diagram right there. I'm going to cut it and look at everything to the right, just like we did with the cut at point H. So if we go down here, I'm going to draw a little diagram. Oops, draw it in red. Do something like this. So we've got this pipe. Again, similarly to point H, we've got this double vector arrow or a torque acting on the end of 36 kip inches, right? Right-hand rule, my fingers are pointing to the left. So this is 36 kip inches. We have local coordinates, right? X, direction. We also have a axial force of 25 kips acting towards the surface, right? So compression. We also, though, at point B on this pipe, we've got this 96 kip inches. Well, if we curl our fingers in the direction of that arrow, my thumb's actually pointing to the right. So now this stress is 96 kip, or sorry, force is 96 kip inches, right? Acting somewhere in the middle there. I'm going to say that we have a torque acting at point K, right? Acting off to the left. It's a guess at this point. We're going to find out if that's the right direction. And if I have a axial force that's acting to the left at 25 kips, there's nothing else acting on this. I'm assuming my axial force, right, on this other end is going to be acting to the right. Right, of P. Well, if we sum forces in the X direction, we could say that P equals 25 kips, right? If we sum moments about the X axis equals 0, well, we have 96 kip inches that's acting in the positive X coordinate. We have 36 acting in the negative And then I said, I guessed, right? I put my double vector arrow as the torque applied at point K in the other direction, right? Negative direction. So I'm going to write that up as a negative T1. So T1 now becomes 60 kip inches. It's positive. So what does that mean? That means I guessed it in the right direction, right? So it actually acts in this direction. Its magnitude is 60 kip inches. All right. So now we have an axial force, right? P of 25 kips. We know it's acting towards the surface, so it's negative. It's in compression. The area didn't change. So from point H to point K, the stress did not change, right? So we still have negative 8.49 KSI, or in other words, this is in compression. Tau max, TC over J. Now we have 60 kip inches times 2 inches, right? That's the max radius, divided by J is 10.4 inches to the fourth. We get 11.54 KSI. So as you can see, the axial stress, the normal stress didn't change, right? Because we have no axial load between points, right? Between the end of the shaft and then point K. And then torsionally, right? Our shear stress is changing because the torque in our shaft is changing, right? This pipe changes. We have 36 at the end, so we'd have 36 kip inches until we got to this 96. Then this guy's going to switch direction. It's going to run 60 kip inches from here off. Right? Yes?
How come there's not a 96 kip inch force, like a reaction force to it?
Because we are countering the 36 kip inches that was originally on the end of the shaft. You have to look at like a torque. If you looked at a torque diagram, and we started at the end, right? It's acting in the negative, 36 is acting in the negative x direction. So we're going to start out at negative 36. And then we're going to add to it 96 kip inches that are in the positive direction. So it's got to first overcome the negative 36. Right? So it grows. So the total from here to here is 96 kip inches. But what the shaft actually sees is either 36 kip inches or 60 kip inches because we're changing direction on the torque in the shaft. Yeah?
Why is it area negative, or the stress negative?
The stress is negative because if you remember from our axial stress calculations, right, the sign on stress is positive if the force is acting away from the surface, and it's negative when the force is acting towards the surface, right? Which is compression and tension. Yes?
On your first free body diagram, how come the 25 kips is going to the right?
This one here?
Yeah.
Which?
Never mind. I was looking at the other arrow.
Oh, the axis?
Yeah.
Yeah, okay. Yeah, the positive x-axis is off to the right. Our applied force there is off to the left. Anything else? No? Making a lot of sense? Okay, so now we know what the stresses are at our 2 points, right? If we looked at 2 little blocks of material on the side of this pipe, right? We now have the normal stress, which we decided was in compression, and then we have this torsional stress, right? TC over J, which changes in magnitude based on the difference in applied load. So what do we do in this case? Well, if we looked at those 2 blocks, right, H and K, if we were to take those squares out and we drew them, call that H, call this K. Right, so we're just pulling out those two little squares that we drew, right? And I'm gonna start by looking at, okay, what's going on the left surface of this stress block, right? The left surface of H and K. Well, if we look at the left surface of H, we've got that force P applied on the left-hand side, right? And we know it's in compression. So if I looked on the left-hand side of this, I would assume we've got a normal force, right, acting on the left-hand side. That normal force creates a stress, in our case, of 8.49 KSI, right? It's a compression. So the arrow's acting towards the surface, right? We have a magnitude, and then the arrow gives us direction, right? Towards the surface. Well, in order for this little stress block to be in equilibrium, right, we have to have forces equal and opposite. So I'm going to say I've got that same force, right, acting on the other side of this stress block. If we look at H again, right, looking at the top and bottom surface, right, there's no stresses acting on the top and bottom surface of that stress block, normal to it, right? We're not squeezing this pipe vertically. And so I'm going to say that we have no normal stress acting on this surface or this surface, right? But now when we step back and look at, okay, well, we now have a normal stress, but we also now have a shear stress due to the torque that's applied at point H. In order to look at what direction that is, right? We know T2 was acting towards the surface, right? That was our torque. So the right-hand rule, right? It's twisting it clockwise. If it's twisting it clockwise, it's trying to take this material and stress it downward, right, on the right-hand side. So the force is going to be acting downward on the left-hand side of this block. So I'm going to say that we've got a shear stress that does that. And we decided that the magnitude of that stress was 6.92 KSI. Well, we'll talk about this in a second, but for now you can just trust me that if we have a stress like that, in order to maintain equilibrium, we've got to have a shear stress that does this on this face, this on this face, and this on this face. So because we are shearing off the left-hand side of this block, right, we had a torque that was acting clockwise, it was trying to strain and push that pipe downward. So it was putting a stress that was downward onto this face. Because we have that, we're going to have the rest of those three, and we'll talk about that in a second. Similarly, we can do the exact same exercise for point K. We have a normal stress, same normal stress. It was 8.49 kips in compression, or KSI in compression. Compression we know is towards the surface. I'm going to make this out of red. 8.49 KSI, like so. Also, now we've got a torque, right? Our torque that we decided was 60 kip inches. We know that we guessed the right direction, so it was pointing off to the left. Right-hand rule, right? My thumb is pointing in the direction of that double vector arrow, curling my fingers. That means we're actually twisting the end of this pipe counterclockwise, right? Upwards. Surface on the left-hand side of this K, we're actually going to be trying to push upwards. If we're trying to push it upwards, our shear stress is upwards. So it's going to look something like this, right, on that face. You can see that from the free body diagram. Well, if it does that, I'm going to tell you, and you're going to believe me, that the rest of the shear stresses have to do something like that. This is 11.54 KSI. It is a negative shear stress, yes. Because we'll talk about it. We're going to get there.
Okay.
There's a systematic approach to figure out the sign convention for that. Okay. It's on the negative face in the positive direction, and because of that, it's a negative. So we'll go through that in a second. What I'm trying to highlight here is now we have these stress blocks, right? We have normal stress and we have a shear stress. Well, as we saw at the very beginning when we talked about axial forces, and you guys looked in the homework about a weld, and you looked at a weld across a piece of material, right, that wasn't perpendicular. It was at some angle to it. Right? Well, what ends up happening is when you have combined forces like this, if you start looking at an element, say you wanted to look at what's going on along a surface like that. You had two pieces of pipe, you wanted to weld them together, right? But we had all of these loads, we had normal forces, we had torsional, torques on this member. And so we want to look at, say, what's going on a piece, a block labeled L, right? Well, when we take these forces relate to the forces that are at L. And there's a way that we can take this, and as we rotate K, our given angle, right, that we're wanting to look at, we can figure out the forces at L. So what happens if we look at stresses at an element not aligned with the applied forces? What if we wanted to look at that? Wow. Right, we wanted to look at this block L, right? We started with H. And now we want to look at L, right? And H, as we know, has shear stresses that do this, normal forces that do this, normal stresses, that do that, right? So when we rotate this element, it has to maintain equilibrium. What does that mean? Well, that means all the forces and stresses, right, that we had on this block that are acting in the X direction and the Y direction have to be maintained when we're looking at this. This is the same thing that happened when we looked at our axial bar that we cut it a cross section, right? The shear stress that was acting along that plane and the normal stress that was acting along that plane, right? They were just components of the ultimate axial force that was acting on that bar, right? So we have to maintain equilibrium. So we might end up getting, right, we're going to get new stresses. Might do something like this. And new forces. But overall, our stresses are our original forces that were on H before, right, have to essentially be acting on L, right? But we just started looking at different components of them, right? Because overall, the free body diagram doesn't stay the same, or it doesn't change. It's always the same, okay? But what we're doing is now we're just moving the orientation and looking at planes that are perpendicular, right, at a given angle. Maybe this was 45 degrees or something like that. So what are we saying here? Well, we're saying that stresses transform as the element rotates. Okay. And if the stresses transform as it rotates, right, we might be able to calculate stresses at a given orientation, say H and K, right? We looked at those. We could figure out what the stress is on a plane, and then because we figured out what's going on here, we could figure out what's going on the other side. Because we knew the shear stress on one side, we knew the shear stress on the other side. Right? But that doesn't necessarily mean that these are the worst case stresses, right? And as engineers, we need to look at the worst case demands on our materials. And so when we start rotating an element and we start changing the stresses on our faces, there could be a possible combination. Maybe at this orientation, right, we might not find the worst case stresses, but if we rotated this element 33 degrees or 45 degrees, we might create normal stresses that are greater than what the material can handle. But if we analyze it here and we stopped here, we might say that that material is just fine, okay? So that's the important part. That's why we're going to chapter 12. Is where we're headed. So we need to look at worst possible demands at any orientation. We need to transform our axes. Axes, right? We need to transform that axis so that we can figure out what's the worst case demand. And the way we do that is we use Moore's circle. Okay. What's Moore's circle? Well, Moore's circle is a visual representation of the stresses of an element at any orientation. Okay. And that's what we're going to spend quite a bit of time on, stress transformations, because it is so important. Because if you were to stop here, right, we analyze stresses, we know we can do that with an element that's oriented, right, with respect to the forces that we're applying. We figured out there's compression on the one side, right, which means there's compression on the other side. We know that the torsion created shear stresses. We can find a magnitude and direction for that. And then if we just related those stresses back to the allowable stresses of our material, we could inevitably miss a worse demand, right? There could be an orientation where the compression actually grows and it's greater than that. The shear stress might be reduced, right? Because overall we need to maintain equilibrium. So we're not going to create more force than there is. We're just looking at an orientation with which those components of the original stresses result in greater demands, okay? Any questions? All right, I think it'll start making more sense here in a second. So we're done with that. We're going to jump to chapter 12. Particularly, it's 12.1 through 12.11. It's really what we're looking at, okay? This projector box, right, was a big block of steel, okay? And we put a large load on it, okay? Say we put 100,000 pounds on this, right, as a point load. There's going to be a lot of stresses going on inside this block, right? We're going to probably bend the block a little bit. We're going to try and shear the block a little bit. If I took it at the same time and I tried to twist the block, right, then we're going to start putting shear stresses on the block. So we end up with, if we looked at a little cube of this block somewhere inside it, maybe it's the very center of this block, we'd end up with something that looked like this, right? Where we could have normal stresses acting on any of the faces, right? All 6 faces of this cube. And we could have shear stresses that are on each of the 6 faces of this cube, right? We would call this a 3D stress block. In this case, these stresses would come from torsion, axial, shear, bending, right? We can have all of our load sources, torsion, shear, axial, bending, on that block of material, right? We apply some of these load sources to this block of material, and if we look at a three-dimensional block, right, at the middle of this box here, right, we could have stresses on all 6 sides of this little cube. Shear stresses are taus. They're denoted, as you can see here, right? We have tau yx, tau yx, tau yz, tau zy, tau zx, tau xyx, and xz. What does that denote? Well, that means tau yx, tau, it's a shear stress on the y face in the x direction. Right? Similarly, this arrow here is on the y face in the z direction. Okay? Z face x direction, z face y direction, x face z direction, x face y direction, right? So that's how those are denoted. So we've got tau yx, shear stress, on y face in x direction. Okay. Normal stress, a bit simpler, right? If this was sigma x, this is the normal stress on the x-axis, right? Pretty straightforward. In this class, okay, to keep things fairly simple, okay, and honestly, it's not that bad of an assumption we're going to make here, right, with respect to applicability to a lot of conditions and cases in the real world, is we're going to assume plane stress. Plane stress means that everything denoted on the z face goes to 0. So we assume, well, everything on the z face, well, that is sigma z, tau zx, tau zy, right? The shear stress on the z face in the x direction and the y direction. We're going to say all of those equal to 0. Why do we make that assumption? Well, 1, it makes things simpler for us. And 2, a lot of the things that we deal with, right, if we assumed that on, say, a pipe, right, the x and y axis are the length along, there's a distance along the length, right, and then the y axis being, vertically around the pipe. Well, our z axis is in and out of the pipe surface, right? Well, we normally don't, it's so thin that we don't normally get stresses that are acting through the thickness of something that's very thin, okay? And we deal with a lot of things that are thin, right? Wide flange beams, that beam that I had up here when we were talking about columns, right? All of the components of that beam, right? The flange, which is the top and bottom of that beam, the web, right? The vertical member between the flanges, all of those are very thin sections. And so we're going to say the z coordinate is in and out of those thin sections. And so if we're looking at thin sections, we can assume that our plane, we have plane stress where those stresses are 0, right? Or very close to it. Well, you end up getting some of these stresses, and when you start looking at thick plates, right? If I stepped on that block, okay, you're going to get behavior that's happening on all 6 sides of that big steel block, right? If I were to step on. But for most problems we're dealing with, we're going to say that that's 0. Plane stress, we're going to say thin sections. All right. Well, as you guys found when we looked at points H and K just a second ago, right, I was able to figure out the fact that if I knew the stress on one face, I could figure out the shear stress on all the other faces, right? Well, if we're looking at plane stress now, everything on the z face goes to 0. So we're really going to just start looking at this x and y plane, right? There's nothing happening in and out of the page in the z direction. There's no stress There's no strain, or there's no shear stress, no normal stress. And so we're gonna just start looking at these as just a plain block like we did in the example, right, with combined loading. And so if we have, right, we want to know the relationship between tau xy and tau yx, right? How does this force relate to this force? Well, if we looked at a very small area, right? If we're looking at a very small block of this material, right? That H and K that we looked at on that pipe, we're talking a very, very small little point on that pipe, right? So if dx, right, the distance that we're looking at of the dimensions of this little block, dx and dy were small, right, very small. So we assume small area. That's dx, dz, or dy, dz, right? That's the areas over which this stress acts, right? Tau xy is the shear stress on the x face in the y direction, right? And that shear stress, as we know, the force that shear stress creates is the stress times the area. Well, the area over which this shear stress acts is the y distance, right? The height of this rectangle times the thickness of this rectangle, right? Is dz, that's in and out of the page. So that would create a shear force, Vxy, and we can do the exact same thing up here, right? We're looking at dx now is the length over which the shear stress acts. The thickness, right, that would then give us the area over which the shear stress acts is dz. So we can figure out that Vyx equals tau yx times dx times dz. This allows us to determine forces So now we have forces. We can sum moments, right? Because as we know, this block needs to be in equilibrium. We're not talking about things in motion. So this block has got to be in equilibrium. So some of the moments about, I'm going to say the origin, right? Point O, that has to equal 0. Well, these two forces here running along the x and y axis, they have no moment arm, right? So they have no contribution. So what does this yield? Well, this yields that Vxy must equal Vyx. Whoops. Vyx, which means tau xy must be tau yx, right? We're looking at a block, so dy and dx are equal. Looking at the same areas on all four sides. We have the same areas on all four sides. If these forces have to be the same, then that means the stresses have to be the same, right? And the direction of them have to be, right, in a direction that maintains equilibrium, right? So some of the moments, this Vyx, it's acting clockwise, right-hand rule, thumb into the page. Vxy, counterclockwise, right, thumb acting out of the page. And so that's why you get this equal and opposite forces on each side, right? Some of the moments mean that we get our directions on these two. Well, some of the forces, this block can't slide up and down also, right? So if we sum forces in the y direction and the x direction, the forces acting in the x direction are equal and opposite. So Vxy on the right-hand side is going to be equal to Vxy on the left-hand side, and then vice versa, right? On the on the y side of our Vyx and Vxy, okay? So what does that mean with respect to figuring out the signs of our shear stresses, okay, as was asked earlier? Well, now that we know that we're going to have equal and opposite going on for our magnitude and directions, if the positive face has positive stress, right? So positive face has positive stress. Our shear stress is positive. What does that mean? Well, remember our notation for tau xy or tau yx is the shear stress on the x face in the y direction, or shear stress on the y face in the x direction, right? So this tau xy, for instance, right? It's on the positive face, right? It's on the positive x side of this block, and it's acting in the positive y direction. This thing is positive, right? If we're on the negative face and it has negative stress, any guesses of what the sign is for this shear stress? It's positive, yeah. Just like multiplying the negative times the negative, right? So we have a positive times a positive is a positive. Negative times a negative is a positive. Right, so what does that mean? Well, that means tau yx, it's on the positive face in the positive direction, it's positive. Tau xy, right? Negative x face in the negative y direction, this is also positive. These two are positive. Right? We look at the other ones, right? Tau yx, it's on the positive y face, it's acting in the positive x direction, this is positive. Similarly on here, negative x face, or sorry, negative y face, negative x direction, this is also positive. So this is a positive shear stress orientation. So if we run through the rest, positive face has negative stress. So we have positive face, negative stress. This is negative, right? If we have a negative face, and it has positive stress, negative face, positive stress, we have a negative shear stress. So now we know they're equal and opposite on our faces. We know the sign convention for our shear stresses, right? Normal stresses, we already know those. Right? If we look at plane stress now again, back on our axial material that we went over, right? That was all the way back. If we go back to chapter 1, this is all about axial. Right? We had this example here where we had a block of material. Okay? Plane stress, that means that the stress is acting outward of the face of this material is 0, right? This thing's fairly thin. Okay, so we assume that what's going on in this direction is near 0 or 0. Okay? So we have axial load acting on this P. The maximum normal stress acts at a cross section that's perpendicular, right? We did that in class. We had this section that we cut. It was AA, right? Oops. So if axial member loaded in tension our max stress, right, sigma max occurs at face AA. Right? normal to our load, right? And on Wednesday, we'll go through what does that mean as we start adding in additional loads, right? Different load sources and how that changes as we start rotating that element. Don't forget, we have another homework this week. It's due Thursday. It's out on D2L. We also have a quiz. It's due Wednesday through Friday, right? Same sort of setup. And we shouldn't have any homework over the break.